The last normal thing Alex did was close the laptop. It was past midnight in the office at Louisiana State University, the kind of late that stops counting as late and starts counting as early. She'd spent 6 hours cross-checking a light curve flagged by a volunteer on a citizen science project called Planet Hunters. Ordinary people, scattered across the world, scrolling through years of data from NASA's Kepler Space Telescope, looking for the tiny periodic dips that mean a planet has crossed in front of a star. The star was catalogued as KIC 8462852. The volunteers, only half joking, had already started calling it something else in the forum threads, the WTF star. Where's the flux? It sat roughly 1,400 light-years away in the constellation Cygnus, part of a binary system. The main star, an F-type, slightly hotter and more massive than the Sun, with a faint red dwarf companion orbiting at a distance so vast it barely counted as a relationship between the two of them at all. On paper, before anyone looked closely, it was an entirely unremarkable entry in a catalogue of 150,000 equally unremarkable entries. That was, in its own way, part of what made the Anomaly so hard to dismiss. Strange behaviour from a genuinely strange star is easy to shrug off. Strange behaviour from a star with no business being strange is the kind of thing that keeps a research team up at night. Alex closed the laptop because she needed to stop looking at it, not because she was finished. The office was small, one of a row of identical rooms along a hallway that smelled permanently of burnt coffee, its window looking out on a parking lot that had been empty since 8. A whiteboard on the wall still had someone else's abandoned equation on it from a meeting 2 weeks earlier, half erased. Alex had stopped noticing the room around midnight, the way people who work with starlight for a living eventually stop noticing rooms at all. Kepler had launched in 2009 with one job: stare at roughly 150,000 stars in a single patch of sky near the constellation Cygnus, continuously, for years, watching for the almost imperceptible dimming that happens when a planet crosses in front of its star from Earth's point of view. It was tedious, patient work by design. Most transits dim a star by a few hundredths of a percent, lasting hours, repeating on a schedule as regular as a heartbeat, because orbital mechanics doesn't improvise. By 2015, the mission had already confirmed thousands of new worlds this way, quietly rewriting how many planets astronomers believed existed in the galaxy. The mission generated more data than any team of professional astronomers could examine by eye, which was the entire reason Planet Hunters existed in the first place. Zooniverse, the platform hosting it, had discovered something almost as interesting as any individual planet: that ordinary volunteers, given a few minutes of instruction, were often better than automated algorithms at spotting a genuinely strange pattern buried in noisy data, precisely because a machine trained to look for one specific shape will walk right past anything that doesn't match it. Humans notice weird, algorithms notice expected. KIC 8462852 was weird. Here's what you need to know before anything else. Every star Kepler had ever watched behaved according to a small, predictable vocabulary of brightness. Stars flicker slightly from their own turbulence. Stars dim by a fraction of a percent, briefly and regularly, when a planet transits. The dips are small. They're clean. They repeat on a schedule you can set a clock to. KIC 8462852 didn't do that. It dimmed by 4%. Then by 15, then, on a single otherwise unremarkable day in the observing record, by 22. Deeper than any planet, even one the size of Jupiter, could ever produce transiting a star its size. And it didn't repeat. The dips came at irregular intervals, lasted irregular lengths of time, some for a day, some for the better part of a week, with irregular shapes. Not the clean, symmetrical notch a planet cuts into a light curve, but something ragged and uneven, like the star's light was being torn rather than eclipsed. Nothing in the standard vocabulary explained it. Inside the team, the biggest individual dips had already earned their own informal names, the way storms do. Day 792 and Day 1519 in Kepler's observing calendar, the two deepest, strangest dimming events the mission had ever recorded from any of its 150,000 targets, filed away in the data long before anyone had gone looking for them, waiting quietly for a citizen scientist to notice they didn't belong. Alex had joined Tabitha Boyajian's small research group at LSU the year before, doing the unglamorous work every real discovery is actually built from, reprocessing archived data, ruling out instrument error, checking whether a signal was actually just dust on a lens or a cosmic ray hit or the kind of statistical hiccup that shows up in any dataset large enough. That was most of the job, most weeks. Finding reasons a strange thing wasn't strange. KIC 8462852 kept surviving every reason. It wasn't a data artifact. The dips showed up independently in different processing pipelines, run by different people, on different computers, months apart, using different assumptions about how to correct for instrument noise. It wasn't a background eclipsing binary contaminating the signal, a common enough source of false positives that the team had a standard procedure for it. Follow-up imaging with a ground-based telescope, checking whether some other star, too close in the sky to separate from Kepler's blurred pixels, might be doing the dimming instead. That check ruled it out within weeks. It wasn't ordinary stellar variability. The star, an F-type main sequence star, roughly 50% larger and 1,000 degrees hotter than the Sun, sat squarely in the category of stars that behave themselves. Mature, stable, boring by design. This one wasn't being boring. Boyajian herself ran the team through the checklist twice, the way she'd run every anomaly through it for years, because the checklist existed precisely to keep hope from getting ahead of evidence. Bad pixel, cosmic ray, instrument drift, background contamination. Each one got ruled out, one at a time, methodically, the way you'd disarm something rather than the way you'd celebrate something. Alex sat in on most of those meetings, taking notes, watching a graduate student named Michael argue, half seriously, that the team should simply publish the light curve with no interpretation at all and let the rest of astronomy fight over it. Boyajian wouldn't allow it. "If we publish nothing but a mystery," she said, "we're not doing science, we're doing a magic trick. We list what we ruled out, we list what's left, and we let the data be exactly as uncertain as it actually is. No more, no less." Michael grumbled about it for a week, and then, quietly, agreed she was right, the way most people in that room eventually did whenever they argued with her about method rather than results. "If it survives all of that," she told the room another afternoon, "then we don't get to have an opinion about what it is yet. We only get to say what it isn't." By the time the team submitted their paper in 2015, they'd run out of things it wasn't. So the paper did something unusual for professional astronomy. It said, in careful academic language, that they didn't know, and it listed the possibilities in order from mundane to strange. A swarm of comet fragments in a long, eccentric orbit was, they wrote, the most plausible explanation, mostly by default. Everything else on the list was worse. Alex remembers proofreading that section 3 times before it went out, because even in the most careful, hedge-everything academic phrasing, there was a sentence near the bottom of the list that she knew, the moment she read it, was going to be the only sentence anyone outside the field would ever quote. Alex remembers the exact afternoon a colleague called to talk through something he'd been unable to stop thinking about since he read the paper. Jason Wright worked 300 miles away at Penn State, and he'd built a career studying, among other things, the theoretical signatures that an advanced civilization's engineering might leave on the sky. Not as a fringe interest, but as a legitimate branch of astrophysics with its own name, Dysonian SETI, built on an idea that was, by 2015, already 55 years old. "There's a fourth possibility your paper doesn't mention," he said. "You didn't leave it out because it's crazy. You left it out because it's the one nobody wants to be the person who says first." He said it anyway. Freeman Dyson had been, by 1960, already one of the most respected theoretical physicists of his generation, a long-time member of the Institute for Advanced Study in Princeton, the same institution that had employed Einstein. He wasn't a fringe figure looking for attention. He was, if anything, characteristically careful about what he was and wasn't claiming. His original paper on the subject didn't argue that such structures existed, only that if a sufficiently advanced civilization existed anywhere, something like this was a physically reasonable thing for it to eventually build, and that astronomy, if it wanted to take the search for other civilizations seriously, had a testable way to look for the consequences instead of only listening for a deliberate greeting. That distinction, looking for engineering instead of listening for a message, sat inside the same broader question that had occupied Enrico Fermi a decade earlier at that now famous 1950 lunch in Los Alamos, the one where he'd asked, almost offhandedly, "Where is everybody?" and left an entire field of astronomy quietly answering him for the next 70 years and counting. Dyson's proposal was one answer to a version of that same question. If they're out there, and if they're old enough, look not for their voice, but for their exhaust heat, their unfinished construction, their fingerprints on the light of their own star. In 1960, the physicist Freeman Dyson had published a short, serious paper in the journal Science, arguing that any sufficiently advanced civilization, driven by nothing more exotic than the ordinary economics of growth, would eventually run out of energy on its home planet and be forced to harvest it directly from its star. Not with a single solid shell, the science fiction image the idea is usually reduced to. Dyson himself found that version physically implausible, unstable under its own gravity. But with a vast, loose swarm of independent collectors, panels, habitats, structures in countless individual orbits, wrapping the star in a shifting cloud of engineering that would, from the outside, look nothing like a smooth artificial sphere, and everything like a mess. Dyson's insight wasn't really about aliens specifically. It was about physics and arithmetic. Energy consumption on any sustained growth curve eventually exceeds what a single planet can supply, and a star is where the energy actually is. He proposed that instead of searching for radio signals, astronomers should search for stars radiating unusual amounts of waste heat in infrared, the thermodynamic exhaust of a civilization's industry, visible even if the civilization never intended to be found. It was, at the time, a fringe suggestion inside a field that barely existed yet. Wright had spent years quietly rehabilitating it into something closer to respectable, cataloguing infrared surveys, writing papers nobody outside a small community read. "I've spent a career looking for exactly this kind of signature and never finding one," Wright told her on the phone, his voice careful in the particular way of someone who has thought hard about how a sentence might be misquoted. "I want to be careful. I'm not saying I think it's this. I'm saying I can't currently rule it out, and neither can you, and that's a very different sentence than the one the news is going to write." If something like Dyson's swarm existed around another star, still under construction, still incomplete, it wouldn't be invisible. It would block light unevenly, unpredictably, on no fixed schedule, in whatever pattern its unfinished, shifting geometry happened to take on any given day. It would look, from a great enough distance, exactly like noise. It would look, Wright said carefully, like exactly what you're looking at. Alex didn't sleep much that week, not because she believed it. She was trained, professionally and personally, to hold the distance between "cannot rule out" and "probably true," and she held it now the way she'd been taught to. But because the paper had already gone through peer review with no answer, and now there was a fifth possibility sitting on the table that every news outlet on Earth was about to notice, whether the research team wanted them to or not. She lay awake, doing the same arithmetic Wright had already done, and kept arriving at the same uncomfortable, honest place he had. Not proof, not nonsense, just an open question with real stakes attached to how carefully it got answered. They did notice. Within days of Wright's own follow-up paper going public in October 2015, KIC 8462852 stopped being an obscure line in an astronomy journal and became, briefly, one of the most talked about objects in the solar neighborhood. Headlines used the word alien without a question mark. Some ran it as fact. The SETI Institute pointed the Allen telescope array at the star within the week, scanning for artificial radio emission. A separate team, working through the Breakthrough Listen initiative, later checked the star for pulsed laser light, a technology humanity itself had already started experimenting with as a possible interstellar communication method, on the theory that if we might one day signal that way, someone else might already be doing it. Neither search found anything. Alex watched a segment about it on a late-night cable news show one evening, almost by accident, flipping channels while eating dinner alone. The anchor's graphic behind him showed a glowing sphere wrapped in what looked like a spiderweb of light, nothing like the loose, incomplete, physically plausible swarm Dyson had actually described decades earlier. A guest on the panel, introduced as a space researcher with no visible academic affiliation, said the word civilization 4 times in 90 seconds. Nobody on the segment mentioned comets. Alex turned it off before dessert. Online, the story split in the usual directions within days. A subset of commenters treated it as confirmation of something they already believed governments were hiding. Another subset treated any skepticism from the research team itself as a cover-up in progress, as if Boyagin's own caution were evidence against her rather than the entire point of how she was doing her job. A third subset, smaller and quieter than either, simply followed the actual updates as they came, patiently, for 2 years, without ever needing the answer to be dramatic in order to stay interested. Somewhere in the middle, the actual scientific question, is this artificial, and if not, what is it, kept getting quieter, buried under 2 years of speculation from people who would never read the paper the speculation was technically about. Somewhere in that same stretch of weeks, journalists covering the story started looking for a name easier to say out loud than a 10-digit catalogue number, and landed on the obvious one, Boyagin's own surname, attached almost overnight to a star she hadn't sought to have named after her. Tabby's star. It stuck faster than anyone on the team expected, showing up in headlines within days, then in casual conversation, then, eventually, in the team's own shorthand, because fighting it seemed like more effort than it was worth. A Kickstarter campaign, started by Boyagin's team to fund dedicated observation time nobody's existing grant covered, raised over $100,000 from more than 1,700 people in a matter of weeks, strangers who wanted, badly enough to pay for it, to know what was happening around a star they'd never heard of a month earlier. The campaign page didn't promise aliens, it promised data. People funded it anyway, in numbers the team hadn't expected, and didn't quite know what to do with. Alex answered emails that fall from people she'd never met, asking, with real hope in the phrasing, whether this was it, whether this was the moment. Some of the messages were what she expected, earnest, a little breathless, easy to answer with a careful paragraph about the difference between cannot rule out and confirmed. Others were harder. A retired engineer in Ohio wrote 3 separate times, each message longer than the last, describing, in meticulous technical detail, exactly how he thought a Dyson swarm might be assembled, as if the momentum of his own hope could substitute for evidence. A teenager in the Philippines asked, plainly, whether it was true, because if it was true, she wanted to be an astronomer too, and this felt like the reason to start. Alex answered that one personally, and carefully, and didn't tell her not to become an astronomer. She just told her the truth. Nobody knew yet, and finding out honestly was going to take longer than anyone outside the field wanted to hear, and that the not knowing was, itself, most of what the job actually was. There was one more message Alex kept longer than the others, from a man who said he'd stopped believing in very much of anything after his wife died the year before, and that reading about the star had been the first thing in months that made him want to know how a story ended. He wasn't really asking about aliens. He was asking whether it was still possible, at his age, to be surprised by something. Alex wrote back that it was, and that whatever the answer turned out to be, the surprise had already happened. It happened the moment the data refused to make sense, months before anyone knew what it meant. She went back to work. Here's a fact worth understanding, because it's the fact the entire next 2 years of research quietly turned on. If you want to know whether something blocking a star's light is solid, a planet, a moon, a spacecraft, a megastructure, or something closer to a fine mist of particles, you don't need to see it directly. You only need to watch how it blocks different colors of light. A solid, opaque object, whatever its shape, blocks every wavelength almost identically. Red light and blue light get stopped the same amount because geometry doesn't care about color. Dust behaves differently. Fine particles scatter and absorb short wavelength blue and ultraviolet light more strongly than they do longer wavelength red and infrared light, the same physical principle, on a smaller scale, that makes Earth's own sky blue and its sunsets red. It meant the question is this artificial had, buried inside it, a testable question that had nothing to do with speculation. When the star dims, does it dim the same amount in every color or not? The physics behind that test wasn't new. Lord Rayleigh had worked out the mathematics of why small particles scatter short wavelengths of light more efficiently than long ones back in the 1870s, explaining, among other things, why Earth's daytime sky is blue and its sunsets are red. The same physics applied at interstellar distance to particles orbiting a star 1400 light-years away instead of molecules in a planet's atmosphere. Astronomy is full of old, quiet laws like that, waiting patiently for exactly the right strange situation to become useful again. The problem was Kepler hadn't been built to answer that question. It had one broad filter, tuned for detecting the presence of a dip at all, not for splitting starlight into colours. Answering the real question meant catching the star in the act of dimming again, in real time, with instruments built to see colour, spread across enough longitudes on Earth that no single cloudy night could cost the whole campaign its one chance. And the star, having no calendar and no obligation to cooperate, dimmed on no schedule anyone could predict. For nearly 2 years after the 2015 papers, it didn't dim significantly at all. Alex spent those 2 years doing what nobody ever includes in the dramatic version of a discovery: waiting. Coordinating a growing network of professional and amateur observatories around the world, some of them run by universities, some by dedicated hobbyists through the American Association of Variable Star Observers, an organization that had been recruiting citizen astronomers to monitor variable stars since 1911, decades before anyone had a name for the kind of anomaly they were now being asked to watch for. Many of the AAVSO volunteers owned backyard telescopes barely larger than the ones sold to amateur enthusiasts at any hobby shop, paired with off-the-shelf digital cameras and a level of patience professional astronomers, chasing grant deadlines, sometimes envied. It meant whenever the star's brightness started falling, as many telescopes as possible, watching in as many colors as possible, could turn toward it within hours instead of weeks. She wrote automated alert scripts that would text the whole network the moment incoming brightness measurements crossed a threshold. She learned, over hundreds of ordinary nights, to recognize the difference between a real dip beginning and the ordinary noise of a star breathing. Small enough distinctions that for a long time she was the only person on the team who trusted her own judgment about them. There were false alarms. 6 of them across 2 years, each one enough of a wobble in the data to justify waking half a dozen observers on 3 continents, each one resolving, by morning, into nothing: a cloud passing over a telescope in Arizona, a calibration error at an observatory in the Canary Islands, ordinary stellar jitter mistaken at 2 in the morning for the beginning of something. Alex apologized after each one. Nobody on the network ever complained. They'd all signed up for exactly this kind of waiting, and every one of them understood, better than most people would, that most nights spent watching a strange thing amount to nothing, right up until the one that doesn't. In May 2017, the star dipped again. The alert went out at 2 in the morning, her time. Alex was awake for it, the way she'd arranged to be awake for exactly this, for 2 years, on the chance that this particular night would be the one that mattered. It was. Observatories across 3 continents turned toward KIC 8462852 within hours of the alert, catching, for the first time, a dimming event in progress across multiple wavelengths simultaneously. Alex remembers watching the data come in overnight, plotted in real time on 3 separate monitors, the numbers slowly resolving a question that had sat unanswered for 2 years, one incoming data point at a time. Boyargin called her at 4 in the morning, her voice rough with the same lack of sleep. "Tell me what you're seeing," she said, without preamble. "Blue's dropping faster than red," Alex said. "It's not huge yet, but it's consistent across 2 sites already." There was a long pause on the line, the kind that meant someone was doing the same arithmetic Alex had already done twice. "Say it again when we have 4 sites," Boyargin said, and hung up, not unkindly. There wasn't time, that night, for anything except watching the numbers keep arriving. The star dimmed more in blue light than in red, not by a small, ambiguous margin, by enough that Boyargin, presenting the results months later at a conference, could say the sentence Alex had privately started rehearsing for herself as far back as that first sleepless week in 2015. The sentence that meant the story had an ending, just not the one anyone had hoped for out loud. Dust is most likely the reason the star's light appears to dim and brighten. A solid megastructure, Dyson's original idea, or anything shaped like it, would have dimmed every wavelength almost equally. The data didn't show that. It showed exactly what a fine, uneven cloud of particles would produce. Dust, most likely shed by comets torn apart in tight, eccentric orbits close to the star, their fragments spreading into an uneven ring that blocked the light unpredictably, for no more sinister reason than orbital mechanics and time. A separate research group, working independently a couple of years later at Columbia University, proposed a variation worth knowing, that the dimming, or at least part of it, might come from the shredded remains of a moon, an exomoon pulled inward from some earlier, more distant orbit around a planet and slowly torn apart once it drew close enough to the star for radiation and tidal forces to start stripping away its ice and rock, layer by layer, over a very long time. The debris in that scenario wouldn't settle into a tidy ring the way rubble from a shattered planet might. It would spread unevenly, drifting into exactly the kind of loose, shifting disk the color data implied. Chunks of a small, cold world, once whole, slowly becoming the mechanism of its own star's strange behavior. Alex found something almost sad in that version of the explanation the first time she read the paper, more than she expected a purely physical process to make her feel. Not because it was more dramatic than dust from comets, because it meant something that had once, in some sense, been a complete and coherent object, round, cratered, orbiting quietly for who knew how long, indifferent to whether anyone was watching, had ended its existence being slowly unmade, in public, in front of an audience of instruments built by a species it would never know existed, mistaken, for 2 years, for evidence of the very thing it so plainly wasn't. Nobody has fully settled between these explanations, the comet swarm or the dying moon. Both point the same direction. Neither points toward anyone's engineering. Alex read the plotted result from that May night twice before she let herself believe it. Then she sat with something that wasn't quite disappointment and wasn't quite relief in the narrow space between them. The same space, she would think later, that Boyargin herself must have known intimately for 2 straight years of fielding a question she couldn't yet answer. There's a separate piece of the story that came from an entirely different direction, and it made the whole picture stranger rather than simpler. An astronomer named Bradley Schaefer, working independently, had gone looking through something almost nobody thinks to check. a century of archived photographic plates, glass negatives of the night sky exposed by observatories going back to the 1890s, digitized and catalogued over decades by volunteers at Harvard through a project called DASCH, the Digital Access to a Sky Century at Harvard. 500,000 fragile glass plates, some of them over 100 years old, scanned one at a time so their faded silver halide images could finally be measured with modern precision instead of squinted at through a magnifying glass in an archive basement. He measured the brightness of KIC 8462852 across more than 100 years of those old photographs and found that the star hadn't only been dipping erratically in the short term, the way the 2017 event had just explained. It had been getting fainter gradually and steadily the entire time it was being watched. 14% dimmer overall between 1890 and 1989. A slow fade with nothing to do with the sudden dramatic dips, running underneath them the whole time on a timescale of a full century, for reasons the dust explanation alone didn't fully cover either. Alex remembers bringing the plot to Boyajian's office, the two of them standing over it the way people stand over an X-ray, looking for what it isn't rather than what it is. A comet swarm doesn't do this, Boyajian said, tracing the century-long decline with one finger. Not smoothly, not for 100 years straight. This is something else layered on top of everything we already found. Or it's an error nobody's caught yet. Which do you think it is? I think, Boyajian said, that I've stopped assuming I get to know which one it is before the data tells me. That's not a dodge. That's the actual job most days, sitting with a question longer than feels comfortable because the alternative is deciding the answer before you've earned it. Nobody has explained that part completely, not yet. The comet swarm and disintegrating moon hypotheses can account for pieces of it. Neither one, as of the most recent published research, accounts for all of it cleanly, and some researchers have quietly wondered whether Schaefer's measurement itself, drawn from imperfect century-old glass plates, might carry systematic errors nobody has fully characterized either. The kind of nagging, unglamorous uncertainty that never makes headlines, but that real astronomy has to sit with anyway, sometimes for decades, without ever getting to close the file. Alex kept a printout of Schaefer's plot pinned above her desk for the rest of her time on the project. Not because it was proof of anything, but as a reminder that even after the exciting answer gets ruled out, the boring answer still owes you a complete explanation, and sometimes it doesn't fully pay that debt. There's a question worth sitting with before we go, and it isn't really about one star. Carl Sagan once wrote that extraordinary claims require extraordinary evidence, a line that gets quoted constantly and understood properly less often than it deserves. It doesn't mean extraordinary claims are false. It means the burden of proof scales with how much the claim would rewrite what we already know to be true, and that burden isn't an insult to the claim. It's the only honest way anyone has ever separated a real discovery from a beautiful story. Boyajian's team never treated the megastructure hypothesis as an insult to consider. They treated it as a claim that, if true, would be one of the most important observations in the history of astronomy, and precisely because of that, it needed the highest possible standard of evidence before anyone declared it real. 2 years of waiting, coordinating, cross-checking wavelengths across 3 continents. That wasn't caution getting in the way of wonder. That was what taking the wonder seriously actually looked like, in practice, at 2 in the morning, for years at a time. For 2 years, thousands of people who had never touched a telescope funded, followed, and hoped for an answer to a question about a star they would never see with their own eyes, because the possibility on the table, however unlikely, however carefully hedged by every scientist involved, was large enough to matter to them anyway. The answer that came back wasn't the one that made headlines the first time. It was dust, comets, ordinary astrophysics, running for at least 100 years in a pattern nobody has fully mapped. That's not a disappointing ending. It's the only kind of ending real investigation is capable of producing. The kind where the universe doesn't owe you the answer you were hoping for, only the one that happens to be true, arrived at slowly in real color data gathered across 3 continents at 2 in the morning, by people who kept watching long after the exciting version of the story had already been written by everyone else. There's a parallel worth naming here, one that keeps surfacing whenever a story like this gets told carefully enough. 230 million years ago, a different Alex stood on the supercontinent Pangaea, in a world still assembling itself into something that could someday support a species that asks questions like this one. More recently, another Alex stood at a polar station and watched a planet that had, impossibly, stopped turning. More recently still, a third Alex found a half-billion-year-old probe drifting silent at the edge of the solar system, carrying a message that arrived far too late for anyone to answer. If any of those stories sound familiar, it's because they're the same shape wearing different clothes. A mind reaches toward the edge of what it can currently explain, finds something that briefly looks like it might mean everything, and then has to sit with what the evidence actually says once the excitement settles. The zoo of explanations always sounds similar for a reason. Coincidence before conspiracy, natural process before intention, silence before signal. Not because the universe is stingy with wonder, because it doesn't organize itself around what would make the best story for the species doing the asking. This Alex spent 2 years staring at a star that never once, in the end, turned out to be anyone's mailbox, anyone's harvest, anyone's home. Just dust and comets, and possibly the slow, unwitnessed death of a moon, and 100 years of quiet fading that science still hasn't fully mapped. Every one of them learns some version of the same thing. The universe rarely answers the question you asked it. It answers the question that turns out to actually be sitting there, waiting, whether or not it's the one you were hoping for. And every one of them, faced with that, kept working anyway. Not because the extraordinary answer arrived, but because the ordinary one turned out to be worth finding just as badly. One question before we go. If you spent 2 years of your life hoping for a specific, extraordinary answer, and the universe handed you a smaller, stranger, more ordinary one instead, dust, not a Dyson swarm, comets, not a civilization, would you call that 2 years wasted? Or would you call it the only way anyone has ever actually found anything true? There's a version of this question that isn't really about a star at all, the same way the earlier one wasn't really about aliens. Most of what anyone spends years chasing, a diagnosis, a cause, a person, a reason something happened the way it did, resolves, if it resolves at all, into something quieter and less cinematic than the fear or the hope that drove the search in the first place. The chasing was rarely wasted. It was usually the only available way to arrive at whatever was actually true. Nobody gets to skip the 2 years and go straight to the answer. The 2 years, uncomfortable as they are, turn out to be the method, not an obstacle to it. Write it in the comments. KIC 846-2852 is still out there, roughly 1,400 light-years away, still dimming on no fixed schedule anyone has cracked, still fading, slowly, the way it has been for at least 135 years, and probably much longer, for reasons that remain, even now, not entirely explained. Observatories still check on it. Alex isn't one of them anymore. She moved on to other stars, other anomalies, the way the work always requires. But somewhere, a much smaller and much quieter network than the one that formed in 2015 is still watching, still waiting for the next alert, still ready to turn instruments toward the sky at 2 in the morning on the chance that tonight is the night it finally answers the part of the question nobody has closed yet. It's still doing the only thing it's ever done. It's still keeping part of the answer to itself.